Dr. Chakraborty, for being available to do this interview with us. As you know, we received a grant from the AI Tennessee Seed Initiative to essentially understand AI-related projects, and the questions we have are related to AI ethics. And so we would like to add, we have prepared some questions. AJ and I will both ask you some questions at any time. If you have questions, please feel free to ask that. Also, if you have additional things that you would like to add to any of the responses that we're not asking, please go ahead.
Sure, yeah. Well, my full name is Subhadeep Chakraborty, but I usually go by Subi. And I have been a professor, associate professor here at the University of Tennessee in the mechanical engineering department. And most of my work is in AI or some sort of machine learning. And I have been kind of working in this field for a while now. It started with self-driving cars. I have been really interested, and I have a lot of projects in self-driving cars. And I also have a completely different direction of research in my lab, which goes towards response to active shooting incidents. I don't know if you have followed that. It started with an NSF project that we have had since the last 4 years. It has ended now, and now I'm continuing to work with the Department of Homeland Security. And since this is about ethics, I think there is a big part of ethics in that research. So what I try to do there is, in case of an active shooting incident in real time, while that kind of event is going on, try to look at camera images from webcams and security cameras, kind of use computer vision to detect where the shooter is, and then tell the people their best course of action in real time. So some kind of suggestion that is a little bit more in-depth than just run, hide, and fight, which is the usual norm. And there are many ethical questions in there as well. Also, in the self-driving car world, I'm sure you have heard of the trolley problem. It's a very old problem, and that kind of crops up in pretty much all aspects. Wherever you want to optimize something, it's usually a zero-sum game, in the sense that you are sacrificing something for something else. So it's a very interesting topic. It's a very tangible and close to our heart kind of topics, both of these. And the one that we are talking about today, that's a little bit different. It's on additive manufacturing, and that's an area I think has a huge potential for AI. So I've started kind of delving in it, and with the seed fund, we have made quite a bit of progress. We are entering into a lot of nice collaborations and partnerships with a lot of people. So it's a work in progress, definitely.
Yeah. Those are both very interesting areas, and I'm looking forward to hear more about them, especially like the shooting one. I think everybody's kind of personally.
It is, right. It's very personal to probably all of us, right? Yes. Sure. So when we wrote the proposal, my main collaborator is Dr. Babu, Suresh Babu. And I have been talking to him about this idea for a while now. Even before I wrote this proposal, we have been talking about this, because it's something that both he and I wanted to do for a long time, and we still want to do, and kind of see where it leads us. And then I also have Dr. Compton from our department, and Dr. Pum Kim from ORNL. But that team has kind of expanded now, and I also work a lot with Dr. Bradley Jared in our department. And now I don't know, it's very recent, so we are writing a huge proposal to DARPA. It's called DARPA SARGE, and that has, I don't even know how many institutions associated with it. So it kind of, well, not this project, but because of this project, there are parts of it that we can contribute towards. And I'm also working with Dr. Thorsten Wust, he and Bradley. So, kind of another NSF proposal that is in the works. So it has kind of, gone in different directions, this seed of an idea. So I think, in that aspect, it has been quite successful, that we have been able to take the findings and the ideas and reach out to different people.
I have a follow-up question. Since you early on mentioned that you see all the AI, all the ethical implications in your work, do you have anybody with that expertise in your team?
Not in this team. I definitely do have for the active shooter project. And so we have, so this was a project in collaboration with Iowa State. So we had people from the education department, someone who could actually go and talk to the school principals and the end users. And we also had kind of like a technical supervisor, if you will. So someone with experience in, just give me one second, I'll turn off this, with experience in teaching these kinds of active shooter drills and techniques to other institutions. So we had a big team kind of helping us with that. That's always fun. I have a third grader, so it's just yeah, going to fourth grade. So we have these conversations a lot. So okay, so let's see. Think about it as a cooking, and I think it's a very valid analogy for any kind of manufacturing process. So if you're doing additive manufacturing, the idea is that you have to get your recipe just right. And by recipe, I mean you have to get the right settings for your machine that is going to print the part. You have to get the right, amount of laser power output, the hatch spacing. These are, the technical things that determine how the building will proceed. If you get any of it wrong, then your product will not be as good as it could have been, right? And there would be defects, there would be pores, it won't be strong enough, you won't be able to put it in an actual, working environment. So if you think of cooking, it's kind of like that, right? You have a recipe for a cake and you have to, use just the right amount of butter and flour and, sugar and salt and, set the oven at exactly the right temperature and take it out at the right time. You get any one of them wrong, and then your cake is ruined, right? So it's kind of the same thing. The only thing is that we have had experience that has been handed down to us over many people, many generations. So we kind of know, and we can just go online and look up a good recipe for a cake. The problem with additive manufacturing is that this is a very closely guarded secret, because companies spend a lot of time and money in perfecting their recipe. So someone cannot just start and enter that market without investing a huge deal of money. The other part of it is the abundance of sensing that has become accessible nowadays, right? So you can kind of keep tab on your build while it is being built. So, like you have an oven thermometer, or you put a thermometer inside the cake as it is rising. So we have, just like that in additive manufacturing and any other manufacturing, to be precise, you have all these cameras that are monitoring the builder. You have thermal cameras looking at the temperature profile, and you have a microphone, or giving you acoustic signals, and you have currents and voltages and all sorts of different signals that are monitoring the process. The thing is, these sensing, these are kind of not complete. Like if you collect data from the Oak Ridge National Lab, the manufacturing demonstration facility, right? They would have a bunch of sensors. If you collect the same data from an additive manufacturing, a small mom and pop type of operation, they will not have those sensors, or they will have some other smaller set of sensors. So you have this whole list of things that need to be perfected, and you have a set of lenses that are kind of incomplete. Now the question is, how can you use this incomplete set of information to make a perfect recipe for your part? So that is what this project is about, if I were to put it that way. Okay, all right. So I think the main challenge is, if you have heard of the curse of dimensionality, it's if you have two parameters, and say each parameter can take on 4 different settings, right? Let's suppose your laser power can go in steps, so that you have 4 different settings that you can turn your knob to. And let's suppose your some other parameters has 3 different settings. So you already have 12 different parameters to test. Now, if you think of the different kinds of settings that you can set your settings at for your machine, you add to that the different kinds of materials, you add to that the different kind of geometries, which is the most difficult part, right? Like if you are building something that looks like a thick block, what you will observe is very different than if you build something that is a thin wall, because all the heat transfer, the way the heat goes through the metal is very different, right? So the main difficulty is that you cannot test just, as you cannot sit down and say, I'll go through all my possible ways of printing this part and I will find the best one. And that is often the case, right? I mean, if you think of any kind of optimization problem that the industry goes through, they have always the same problem. And that's kind of where the whole topic of dimensionality reduction came from, where you essentially try to minimize the number of experiments that you have to do. Now, we are not trying to do that. What we are trying to do instead is develop a model that is generic enough that will be able to predict the outcome of a particular set of parameters. By that I mean, like, let's suppose I want to build the cake, but I do not have to set the oven to 350, 400, 450, and 500. I would know from the model itself the results that the cake will be burnt at 500 and will be underbaked at 250. So I will know that beforehand, and I'll know that because I have seen the data from a lot of builds before. That's where the data comes in. And I also have a pretty good understanding of the physics of the problem. So the new part of my proposal and this idea is that there is a handshake between data and our physical understanding of the process. Usually it is one or the other. There's a huge history of physics-based understanding of these processes. Welding literature is so rich. So we know how to model the fluid movement, the heat transfer. There are these well-established theories, so we know that. The only thing is that they work for a limited set of situations. If you have a simple geometry, it gives you good results. But as soon as the geometry looks different, it might look different. And also, these are very time-consuming models to run. So, they will take hours to run, because these are usually finite element models where you split up a whole section into different nodes and you run a huge number of calculations to get your overall understanding of the process. So these 2 things. One is that, it might not work over the entire domain of operation. And secondly, it takes a long time to run. Those are the problems of your physics-based model. The problem of data-driven models is that you do not have any understanding of the physics. You're just building a model, which is the AI part of it based on data, right? So what we try to do is kind of have both. So we learn from the physics, but we also use the data in real time, and thereby come up with a model that we will be able to predict what will happen over that large number of parameters. I think these 2 things go hand in hand, right? I mean, it's the only difference is the time frame that we are thinking of. I mean, if it never improves the quality of life at any point of time, then I don't think that research, would be worth doing. Even something that is, as obtuse as, I don't know what the example I would give, finding the mass of a dying star, like 3.5 billion light years, even that has some, some level of impact on some other things, right? Anyway, that's beside the point. But I think this is mostly research at this point. It's fundamental research. We are trying to understand physical processes, optimization, machine learning. But at the end of the day, there is this idea that we want to kind of democratize the process of additive manufacturing, so that we don't need to have that kind of high entry bar to someone who wants to set up an industry or set up a shop where they will do additive manufacturing. And I think that ties into some of the goals of the industry as well, that we can do this in a more reliable manner, right? The parts will have fewer faults, which means once you build something, then it will be able to be put in, in use without going through a lengthy certification process. One of the challenges of this is that there is a huge, long drawn out certification process. So if you let's suppose you have done all of this, fine tuning your parameters and you're producing parts, it has gone through the vetting process, you know that your build is good enough for putting in a submarine or an aircraft or something. Now you change something very slightly, you change the part geometry or the material, that whole process has to be repeated again. So there is a huge cost associated with that. And something that this will help with, hopefully at some point, is that process can be shortened, that you have more confidence in immediately in what you're building. So for businesses, I don't think I'm the right person to really answer that question, because again, my involvement in this is more from the AI and machine learning side, and I know that the state of the industry in additive manufacturing and manufacturing as a whole, that's a complex economics question. So I don't think I should answer that question really. But very naively speaking, I think this will enable a lot of smaller industries, like small businesses, to be able to compete in this space. I think that is personally what I think is going to happen. And the other thing is, even for bigger industries, I think like I said before, it's going to shorten the time from your conception of a part and process to where it can actually go into a deployed part. And the benefit of additive manufacturing is that if you're building 1 million parts, probably additive manufacturing is not the right tool for that, right? You want to batch process it you want to use conventional manufacturing processes to produce that part, like in an industrial setting. So these are often one-off parts, right? I mean, something that you have seen and heard of these really interesting, cool ideas, like you send one of these machines to Mars, and you can actually build things there as and when you need it. So it's kind of, or an additive manufacturing machine that builds itself or builds a bridge while it is on the bridge. So those kinds of very unique situations where you want one part, but that part has to withstand the loading and the use that it is going to be subject to. So I think that's kind of the importance of being able to do this reliably. I don't know if that answered your question, but that's the best I can do, I think.
Well, I mean, the way you're explaining it, sort of, to me, it seems like something that would potentially be very useful in defense.
Yes,
Right?
yeah,
Like
absolutely. You're absolutely right. Yeah.
like spy situations and situations where they're, that they can go in a place and then build the thing that they need to build without having to worry about detection and those type of things, I think.
I'm not specifically aware that there is an interest, but I know that there a lot of funding comes from like DARPA is funding this one, right? So definitely, I think that's maybe what is working towards that interest. But yeah,
To me, that's kind of seems like. I mean, I'm sure there's a many other more commercial, but this also seems like very defense type of work too.
yes. Well, the way AI works is it essentially learns a relation from data, right? I think that's kind of like the broad definition of what it is trying to do. Even if you think of like the highest level of AI, like ChatGPT 4, right? Or something that is, really top of the line AI, they are essentially consuming a large amount of data, and they're trying to find and build relations and be able to extrapolate them. Now, for most of these kinds of system, and I know that there's a huge amount of push towards explainable AI, is something that you will be able to predict what the AI is doing and understand why it is doing what it is doing, right? But that is, I think, the main challenge in the AI world is that I think the whole AI research has kind of moved from what can AI do to how do you know what AI cannot do, or where is it going to fail, right? So for self-driving cars example, I think that's a easier place to give an example in. So we all know that like Tesla and all, they have these autopilot, right? And it works 99% of the time. The question is, when does it not work? And that's a difficult question to answer. A lot of research has gone into a very like subset of this question, right? Okay, what happens if I add a certain amount of noise to the image, right? Let's suppose I put some kind of high dimensional noise to the stop sign, right? And it takes a picture of the stop sign, but now it doesn't know that it's a stop sign, it thinks it's something else, so it doesn't stop. And the consequences are pretty drastic, as you might imagine. It will go and go into the intersection without stopping. So that is one of the main challenges, that it's very difficult to find the operational envelope of AIs. What happens at the edges? What happens when things are not exactly squarely in the middle of what you have trained it to do? And why does it fail the way it fails? So that is one of the main questions of AI. And there's a lot of effort from NSF and fundamental research organizations who are trying to understand that question. So in NSF there's a program called SLES, Safe Learning Enabled Systems. So any learning enabled systems has the problem that you cannot define its safety very easily, and there's like cutting edge research going in that direction. I think that same question is here as well, right? I mean, let's suppose you only rely on data. That means that you have fed it your model, this huge amount of data from parts that you have built earlier, right? And it has built correlations as to what the thermal signature of that part is going to be like based on your input variables, right? I mean, if I do this, then this is what I'm going to get. But because if you do not regulate that learned system, then it can give you some very drastic and probably very wrong answers, and that can be quite disastrous in the sense that, let's suppose, in an extreme situations, you're saying that, well, I have complete confidence on my machine learning system, and it is telling me to build my part using these set of parameters, right? Let's suppose I do that. And I said, I have so much confidence that I'm not going to test it. I'm not going to go through that same certification process that I was talking about earlier. And I take that part and put it somewhere. But maybe that machine learning system, because it hasn't been verified, is wrong, and you get a failure at a critical point in a critical part, right? So it can have quite disastrous effects. And I think that's kind of like one of the main ethical problems with AI, that it's not very easily explainable. It's usually thought of as a black box. You're training like millions of parameters, right? So it's hard to understand exactly what is going on.
The data quality as well, right? Like,
yes, absolutely. Absolutely. The data quality it's a little more technical, but that's one of the problems specific to this particular field, that when you're training, you want a balanced data set, right? That means you want an equal representation of different kinds of things that can happen. Right. Now, if you think of a part that is being built, 99.99% of the time, that part is going to be fine. That means your data set, most of it is good data, and you have a very small sprinkling of defects and errors, right? That means if you think of it, let's suppose I just tell my machine learning system to be able to classify whether the part is good or bad. Now it will just say everything is good, because automatically it is guaranteed a 99.99% success rate, right? So but I don't care about being successful 99.99% of the time. I'm just interested in the parts where it is going to fail. So that skewed data set, like you're saying, the quality of the data is going to be very important. And that's true in most cases, yes.
And that's the kind of the common thread across all like AI projects is this
Yes.
all about data. And it's sometimes it's the data sets have been created by, back-end developers or people identifying things and tagging them, naming them, versus sometimes it's automated data collection. And
Right.
I think automated data collection, as you were saying, is very very good. It's all the good cases that are
Right. Right.
there, which impacts, I think, the
Yeah.
probability of detecting any bad.
You're right. And I have many anecdotes about that. The problem is that these are, again, these are mostly anecdotal. Like there's one where self-driving cars, they do not typically work well where people are wearing orange colored clothes. The reason is because it's not a common color, other than in
But
the
it's
UT.
what construction workers wear.
That's exactly right, right? So you have that problem that your data set does not have enough representation of
Yeah.
that orange colored clothing, but it is super important because that's what construction workers wear.
And
So
they'll be wearing it and the car is going and not recognize them. Yeah.
right, exactly right.
Thank
So
you.
there are all these problems with the data set that, but if you did not see it, you would not think about it unless, it just,
Yeah.
yeah. So how do we kind of,
They need to train on UT people.
yeah, yeah, that's what we say. That's what we say. Exactly right.
It's all orange there, so much orange.
Yes, yes.
So we have a few more questions.
Mm.
We're also getting close to our time. So I think we've talked a little bit about the ethical considerations and concerns that apply to your project. Can you elaborate on that a little bit? So help us understand how you think about the ethical concerns and,
With
how.
this project, not so much. I mean, I'm again, because this is fundamental research, not really that much concerned about ethical concerns here. Like I said, the main concern would be uh, if you were trying to guarantee something that this is going to be good enough for you know like a production part. That is a really difficult problem to solve, and you have to be very careful before making a claim like that. One thing that I would say is when you the way that the new thing that we are trying to propose here is that we are using both physics and data. So that gives us some confidence that what we are doing essentially has the benefits of both. It's not going to do something that is, in an extreme case, if you're just using data, right? Your process can, let's say, come up with a result like that does not make any physical sense, like that's a negative mass, right?
Absolutely.
But if you have a energy conservation equation in place and your machine learning model is also taking cues from there that I cannot do that because it violates the findings of physical laws, then at least you are making sure that those kinds of mistakes are not made. But still, at the same time, ultimately, what you're teaching, what your model looks like, is a deep neural net, right? So it has many nodes, many parameters, and all of them together is giving you these really interesting outputs, right? So that's a problem. Now, there is one more aspect of it that I did not really talk about, which is the real-time control aspect of it. So, when we are building, usually it's a static process. So you set the parameters, you turn your knobs, you make it like what you want, and then you let it run, right? It just prints the parts. But if we could use this learned model of the system and use that in a feedback loop, like what they use in automation and control systems, then we can essentially write or correct those mistakes as they are being made. Because remember, we also have sensors looking at them, right? So all of these are nothing is direct. I mean, you don't really see a microscopic 50 micron pore. It's just impossible to see it unless you do microscopy, and that's just not possible in situ. But at the same time, you have these clues from the heat signature, for example, or the acoustic emissions. And with the model that you have trained so carefully, then you can go and change something, maybe when the next layer is writing, that you go and fix it in real time. So it's kind of like the whole idea that would make it really neat.
That's quite amazing. Yeah, that's very amazing. So in this way, so you're talking about like, okay, we use data, we use all these different data points, and then we use physics. But physics just becomes one more data point, right? Like
Pretty
whatever is
much.
in physics, it's just additional variable, but it confines the physical, like what can happen and what cannot. So it cannot go absurd because of that. In normal cases, it does go absurd because it has no boundaries.
I mean, it does not, because you would want to make sure that you place constraints and bounds so that it does not do that. But one of the more, I think, elegant ways of doing that is using the physics, like you are saying, as another. It won't be a data point, but it would be another factor that it considers. Usually it's based on minimizing a loss, right? There's a loss function at the end, and you're trying to minimize the loss, and you adjust the weights and in your deep neural net so that that loss is. Now that loss usually comes from a mismatch, right? What the model is predicting and what your data is. But here we are also putting in another loss that is based on what the model is predicting and what the physics model is predicting. So it's essentially just an additional term that makes sure that we don't go too far out of the realms of possibility. Yeah.
Yeah, very interesting.
It's a
Anything
relatively new idea, this thing. It's 2019 is when it came out. It's called physics informed neural networks. So now it's like exploded. It's like physics augmented and physics informed and so on and so forth. There are a bunch of these now. About the project, not really. I think we have covered the basic aspects of it. Since this is, well, I kind of interpreted outreach as something like that, like what we can do to do outreach. So I think there was a conversation I had with, my next door colleague here, Dr. Young, and he and I were talking about, how to kind of bring this kind of approach beyond, because these machines are very expensive, right? I mean, not too many people can actually stand next to a metal additive manufacturing machine and see it in operation. So we were thinking, like, using these virtual reality headsets, and using some kind of a binocular vision camera, you can get 3D content, and that might be a very interesting way of providing these kinds of experiences to people who might be interested, but they don't have something close by that they can go and watch. So I thought that was a outreach wise, it's a pretty interesting thing. Maybe we can, yeah, do it some.
Absolutely. And I think, even like working with either public libraries or other public stakeholders where these could be demonstrated, even in virtual way, I think would be amazing for outreach, for reaching to
Right, right.
areas where they might not have this kind of.
Yeah, and this is ubiquitous now, right? I mean, this Google Cardboards. I think like New York Times or something like that. They had this thing, so they put these folded up Google Cardboard in their newspaper, like the physical paper newspapers, and distributed it. And so everyone had a copy of that, and you can just fold it back into the shape and put your cell phone inside it. I don't know if you have played with one of those before. My son loves it.
I have
So,
not.
yeah, because there's so much 3D content, right? I mean, you can just put your cell phone in, and what it does is it's essentially, it splits the screen into two, and there's a lens, and you put your face in it, essentially just like like the HTC Vive or the Facebook, the Meta headsets work. It's just cardboard, so it doesn't cost anything. So
Wow.
you distribute that, and everyone has a cell phone. So you put it on YouTube, and people can just watch it.
Yeah, I gotta find that. My boys will love it too.